Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Marvell with George Hervey, who's going to talk about the disaggregation of the network and what's changing on the networking space. So, George, we've been seeing a lot of disaggregation in the data center. What's happened there, and how is that starting to roll into the networking space?
So the data center has first started at the server level, disaggregating, separating the software from the hardware, and then eventually separating the network connectivity from the processing power inside the server.
So, what's driving that?
A lot of it is the hyperscale cloud vendors are disaggregating their data center to give them more choices and more vendor selections.
And is it a question of throughput? Is it a question of just many different options of what they're trying to get to? What are you seeing there?
It's the scaling of the applications in the cloud. There's more and more applications being punted to the cloud, and so these data centers have to grow in scale and in compute power in order to address the scaling.
So we've seen a lot of that work being done on the server side, but the networking side has pretty much been ignored. Why and what's changing there?
The networking side was pretty much dominated by a few OEM players in the network space, and as the buying power of these hyperscale clouds grew, they were able to generate a market that allowed them to disaggregate the software from the hardware, giving them more choices.
Why don't you draw this out for us?
Sure.
So what are we looking at here?
So what we're looking at here is a typical 100,000 server deployment in a data center. It's usually built with 2,000 racks with 48 servers per rack. Each rack is populated with a leaf switch or a top of rack switch, and that top of rack switch enables the connectivity within the rack and then uplinks to the spine.
You've drawn out a top rack switch there. What does that do?
That top of rack switch allows for connectivity within the rack and links also to the data center network.
This is all Ethernet?
Everything here is Ethernet now.
We all thought Ethernet was going away. It's been around forever. Is there any prospect that it will continue to grow and stick around?
Actually, we see massive growth in the Ethernet industry. We see more applications being deployed every day, as well as new port speeds being introduced as these applications require them.
So we've had this sort of monolithic type of network box up there. Now we're starting to get some granularity in here, which is pretty much consistent with what's been going on in a lot of other areas in electronics right now, where we start adding that granularity in and get some efficiencies. How does that apply into the network racks?
So the network racks, there are different use cases and different applications that are being deployed. A server can operate at 10 gig, at 25 gig, 50 gig, and in the future even 100 gig. So we see a variety of port speeds being deployed at the server level, and so the top of rack switch allows for the connectivity between those speeds and then to the main network.
If you were setting up a rack today and you had those choices of the different speeds, would you necessarily get everything at the latest speed, or would you mix that up?
So the challenge today is the development of the ASICs that go into the top of rack are a long design process, and they have limited, at the time you design them, you have a limited scope of port speeds that you have to choose to support. And so you end up usually with a superset of what is required.
So in 2012, we saw the introduction of the 802.1BR standard. What did that do?
802.1BR fundamentally changes the controlling bridge processing element of the network. It allows you to implement port extenders with a control bridge as a separate processing unit.
And so what does that really mean for the guys who are running these data centers?
In this example here, we see the 2,000 racks, and rather than having to control and manage each of the racks, each of the switches at every top of rack, we can now manage it from a higher level of the network with fewer devices.
And so what's the benefit of that?
So from a network management perspective, we've taken 2,000 switches and consolidated them into 4 management points. So higher availability, less configuration, simplified management.
You get a big power advantage out of doing it that way as well?
Not today, no. Today, the devices that we use in these boxes are still the same device in every layer of the network.
So what can be improved here? I mean, where do you get the gains in efficiency and maybe even performance?
Sure. So in this top of rack switch, actually, when it's operating in a port extender mode, there are far fewer functions that it must operate. It doesn't need to provide local switching. It doesn't need to have complex management tables. So it can be simplified and reduced to power. The reduction of power here allows more power in the rack to be used for compute and storage services.
This has traditionally been an area that's been ignored, though. Why has it been ignored in the past?
It's been ignored in the past because the devices that were built for these networks did not have a large enough market share to address each of the use cases.
Has that changed?
Yes, through the standardization, it's enabled multiple OEMs to launch 802.1br compliant architectures, and therefore the ecosystem to build dedicated devices to serve this purpose.
Okay, so now you've got everything moving at a higher level. You basically added a level of abstraction here. From that level of abstraction that you've added, what can you do that you couldn't do in the past?
So really, where we see the benefit is on the power and cost savings in this top of rack use case. So as you can see by the sheer volume, making a major power and cost impact at the highest volume node in the network, it offers a tremendous savings to the network operators.
So where do you see this going next? How does this start playing out in potentially other markets?
As we see in IoT and in automotive, the number of endpoints, Ethernet-based endpoints, is growing exponentially. And without having to build more and more switch silicon and more switching systems, the idea of a port extender can attach to this breadth of products.
And so this stuff gets embedded too, right? It doesn't necessarily have to be a discrete unit that sits on top of a rack. This stuff can actually be built into a whole system much more easily.
Yes, actually the biggest benefit is when we do it at a system level, because not more than just the benefits of the chip and the optimizations in the chip is the savings on the hardware and the ecosystem of fans and power supplies that can be achieved through this reduction.
One of the problems with doing everything wirelessly is that it's open to cyber attacks, and we've heard a lot about security in the IoT world, IoT as well. What does Ethernet provide that it didn't, that the wireless cannot?
Well, wired Ethernet allows you to have a point-to-point connection. Ethernet is a point-to-point technology. It's not a point-to-multipoint, so you know what devices are on each endpoint.
And Ethernet is fairly well established. It's still more expensive than a lot of other types of communication. Is that cost coming down as well?
As Ethernet continues to grow, the economies of scale bring the price of Ethernet down.
And one other piece that goes with this is Ethernet itself is not static. It's been improving in terms of throughput on a pretty regular basis. Is that going to continue as well? Has it hit a ceiling?
We believe that is where the biggest investment in the technology is being done, is improving the hyper growth. As these more and more applications move to the cloud, there's a need for exponential growth of the network that cannot be achieved through purely Moore's law or silicon improvements.
So one of the big concerns inside of data centers is operating expense, the OpEx, and also the CapEx goes with that, but the OpEx is really becoming much more of an issue, particularly from the standpoint of how much does it cost to power up these systems, how much does it cost to cool them, how much does it cost to actually run them on a regular basis. What does this do to that equation? How does it affect it?
Well, this is one of the key highlights of this functionality is when we do a purpose-built port extender, we are able to achieve low power levels that improve the utilization of the network. So more power is available to be used for computing and other services rather than being used in the network.
And that utilization is a key number that's pretty much been ignored by a lot of people because that's really what determines the efficiency in the data center, right?
That's right. And data centers are measured by their PUE, their power efficiency. Networking is seen as an adder on top of whatever the baseline is.
So we're used to thinking of power in terms of the servers, but how much does the networking piece of this add?
So we look at the networking as consuming around 10% of the total power of the data center. And by achieving a greater than 50% power reduction, we're equivalent of 5% of the total power. So 5% of the total power of a 20 megawatt data center is a full 1 megawatt.
And that's just in terms of the powering up, right, and running these things. You also have the cooling costs. You also have some other the constant running of these things. This is a number that's generally underrated.
Yeah, so it's a significant portion because if you can add 5% more servers, if you can allocate 5% more power to your servers, you can provide many more services in the same power envelope. And these data centers are limited by the power envelope of the local utilities that are near them.
George Hervey, thank you very much for a great explanation.
Thank you.